Today we have Dr. Geetha Manjunath with us. She's the founder and CEO of Nirmani Health Analytics, which is developing a novel solution for detecting early stage breast cancer using machine learning. She has over 25 years of research expertise in IT industry and has proposed and lead multiple research projects in artificial intelligence, crowdsourcing, cloud computing, etc. So, Dr. Geetha will be speaking on AI-based changes brought in for healthcare. Welcome, Dr. Geetha. The stage is all yours. You may please begin.
It's great to be speaking with all of you. Yes, I'm going to talk about use of AI, particularly what's called as machine learning for healthcare applications. Yes, I have a PhD from Indian Institute of Science, and I'm the CEO and founder of Nirmani Health Analytics, where we are developing AI-based medical imaging applications, particularly for breast cancer. Data is available everywhere. Of course, data is also available in healthcare. The data could be in the form of health plans, the pharma information. There's so much of EMR, EHR data that you have in the hospitals, patient-related data, could be prescriptions, everyday notes, everyday health vitals of the patient. How and where did you get medicine into the hospital? The whole supply chain of not just the medicine, the different equipment that's brought in a hospital. Different charts, right? We have X-rays, the sonos, the MRIs, the CTs, and all of these medical imaging. Different tests like, pathology tests, blood tests, urine tests, all of these things. And a lot of financial data, how much money was paid by the by the patients, how many still pending, all of that, right? Any adverse events, if at all there's a follow-up that is happening. And several such data, including social media data, where patients are talking to each other, doctors are talking to each other, exchanging information about what's the best way to treat the person, and so on and so forth. Nowadays, doctors are facing patients who are more intelligent, than the earlier patients, because they have Google to help them, right? Before they even come to the doctor, they'll tell, these are the 3 medications that are usually suggested by Google, and what do you give, right? So we have intelligent kind of patients as well. So we have all of this data. What do we do with this data? If we are able to utilize this data to provide high quality healthcare in an affordable and an accessible manner, the whole world will be healthy. And that is where AI, artificial intelligence, can make a difference. AI in healthcare has several applications. In each of these, I'm sure, just if you give a 10-minute break, you can write down in each of these boxes some 10 different applications. How smart processing, data processing kind of software can help you serve patients better. There will be several applications. So what I'm going to do today is go one level higher, abstract out across all these applications. What is the base functionality? You will have many talks, many big books talk about AI can be used for this, AI will replace doctor. No, please, it will not replace doctor. Several such applications. But very few talks which will talk about exactly what is AI, exactly what can AI do, what can't it do, and where do the AI and the the doctors or the users come together? Where is the intersection, right? So that is what I hope you will actually take away at the end of this talk. Now, some of you would have heard about this name called big data. Big data, first thing you'll come to mind, maybe there's a lot of data, and that's why it's called big data. Yes, of course, there's a lot of data, terabytes, petabytes of data, then definitely it's called big data. But big data has 4 main characteristics by definition, and people have been adding more V's to it, 4 V's we say. First is volume, the actual size of the data itself. A particular application or a data store is called big data if it also has enough variety. Variety means what? Variety doesn't mean like, one from patient, one from doctor. No. Variety actually means the data type variety, we call it. That is, there is text data, there is image data, there's video data, there's sound, audio data, all of this, and all lab data, and all of this, right? Structured, unstructured. This is called a variety of data. If you have a data store, if you have a database, you have a data pool where you have a variety of data or volume of data, any one of these can be easily solved. But when you combine two of these, then it becomes a very, very smart problem that will be very useful for the society. The third one, veracity. What is veracity? Veracity means data in doubt. That means I have received the data, but I don't know whether it is correct or not. That also is a big data, because using a big data application platform or machine learning, we are able to figure out, right, and help bridge this gap. You received, let's say, you're doing continuous collection of BP measurement, bedside monitor setting. Suddenly you will get a zero. You don't know whether, it's really zero or the machine stops working. That is veracity, right? There again, some of the other modes of functioning, other modes of enough information that you collect from the patient will help you decide this. Fourth one, V, is called velocity. What is velocity? Velocity, we all know, right? It's moving, velocity, speed, and all of that, right? So the V here is the speed. That is basically saying it's not a single point data. It's a running data. It's a continuous data. That is also called big data. So when you hear about the word big data, just I want to kind of, give you the basic definition of this so that big data is not always volume. If you have complicated data with variety, you have complicated data where you don't know whether something is right or wrong, and you want to figure that out as well. And then you have moving data, data in motion, we call it, right? That is also called big data. So this is just to make sure. Actually, healthcare has more complications than just these 4 or 5 things that I mentioned, because here the complication is, where do I store the data? How do I send it? Where do I compute? How much information should I store? All of this is many, many questions a technological, solution provider will think about. Whereas in addition, healthcare has more problems, more challenges for a data analyst. And it's nice to know, because if you're dealing with an AI solution, you should ask this question: how does your solution work with imbalanced data set? What is an imbalanced data set? Imbalanced data set is one simple way of thinking about number of people who are healthy on the world is definitely greater than number of people who are unhealthy. Of course, it depends on level of unhealthiness, mental, physical and all. But roughly, let's say number of people who have cancer is much lower than number of people who do not have cancer. Now, this is good for the world, but it's not good for an AI model that is being built, because it will call imbalance in data set, right? Ideally, if you have equal number of male, equal number of female, you can actually detect whether somebody is male or female. I'm just making up a problem, right? Similarly, if the equal number of cancer and non-cancer, your AI algorithm can be very, very quick. But here you have imbalanced data. You have missing and noisy data. You have even uncertainty in ground truth. Why? Because there is, let's say, a mammography image, right? I work in breast cancer, so I typically tend to take examples from breast cancer. So if there is a mammography image, one radiologist may feel, yes, this is BIRAT 4, BIRAT 5, it looks like malignancy. But another radiologist may say, no, probably let's put it on BIRAT 3, ask her to come back after 6 months, right? So there is also uncertainty in the actual result of the data. So it actually hurts to the problem itself. And there are also a lot of dependency between different data points you're collecting. For example, if you're collecting a lot of data from a patient, right? One could be heart rate measurement, another could be BP measurement. Are they correlated? Ideally, in a mathematical scenario, in an AI scenario, they just have to be independent. They should not be dependent. But yes, the body is so complex that if there is a high BP, there could be a heart problem as well. So there are some intrinsic feature dependencies which are not explicit. So this also makes this a very, very challenging problem. Why am I talking about all of these problems? Because these are some of the questions you have to ask if somebody comes and says, I have an AI solution. Another basic thing that we need to understand in terms of what kind of applications can machine learning enable, especially in a clinical setting, right? See, healthcare can have many, many applications of AI. For example, how do you reduce the waiting time at the OPD, right? And several of these, how do I ensure that the reports are sent within 5 minutes of report availability? So all of these are definitely smart IT systems, but it's nothing special about healthcare. These kinds of things have been done in barbershop, reduce the waiting time. Those kinds of applications can. But I'm going to talk about pure healthcare clinical use of AI today. And when we say AI, you'll ask me, what is the connection between machine learning and AI? AI is a very, very broad umbrella. broad umbrella term where there are primarily three kinds of AI models that are available in computer science. One is called machine learning, which is a subset of AI application. Typically, in healthcare, when somebody is talking about AI, they are talking about machine learning. Here is where you use data to make decisions. You use data and machine learning models to help make decisions for the doctors. Okay, and we'll see a lot more about this and how. There are also systems called rule-based systems, which are sort of using what's called a first order logic and all that. So rule-based systems, which say, okay, they just capture the expert knowledge in the form of rules and run this through it. It's good. But then what happens if something doesn't satisfy the rule, we'll get into an unknown situation. And many times, because the body is so complex, you will not be able to look at all of the different types of conditions a patient may come up with, right? So that is seldom used for healthcare. It's not used. The third one is called semantic systems, where you can, as a doctor, you have a lot of knowledge in medicines or maybe in medical literature, clinical literature, right? How do we capture that in a way that a computer can understand? That's a semantic knowledge, we call it. So these three parts, and typically whenever anybody says AI, they are talking about machine learning, where it's a data-based decision making. So I just don't want to use simple, big words like AI and actually mean machine learning. I'm going to use machine learning. Okay. Even within machine learning, there are different types of applications you can come up with. One, which is very well known, what will happen, predict a future. I've played with and I have developed many types of applications, be it healthcare or several other applications in my 25 years of experience using data. Now, when we talk about prediction, for example, in an ICU, you're collecting continuous data, the velocity data, right? The continuous data. You want to tell when is this person likely to be, requiring very critical attention, likely to mortality prediction also is a possibility. Or if he's in a ward, you're actually collecting health vitals every 20 minutes, let's say. When do I need to shift this person to an ICU? Predict if the person's disease status will become higher. I mean, his health status decreases. So this is prediction. Another way of prediction is nothing to do with time. A person comes in, she gives her mammography, and you say, can the tool predict? That's also called prediction. Because it doesn't know, it predicts whether there is cancer or not in here. That is also called prediction. These are called predictive analytics. This is a suite of things. You can think about in your own domain, you can think of many such things where there is an unknown and the machine is helping you determine that, right? So that is one. So there's this diagnostic analysis saying, why did it happen? So the why did it happen is best explained with a car breakdown, right? Car breaks down and you have to figure out why did this happen. There are several methods. Same way, the body breaks down, you have to figure out why did she faint. There may be several parameters. So this uses what is called as a logic-based analysis. A different type of a network or a different type of a model is used for this. It's called diagnostic analysis. Descriptive analytics. What is descriptive analytics? You have a bunch of patients. You have like 10,000 patients coming in every month. I want to understand what is the profile of these patients. How many of them are male? How many of them are female? How many of them like, let's say, to take tablets? How many of them like to take syrups or whatever? Or how many of them are highly diabetic? How many are not? So you want to kind of describe the data with 10,000 patients or 10 million patients and 1,000 parameters, right? So then what you want to know is like surprise me thing, right? So where you'll say, I want to know, tell me what are the prominent features of this. Then say, okay, here are like 200 people who have, who are likely to get COVID because they have like these factors, and that makes them, high risk for this, right? So that kind of looking at a group of information and coming up with clusters of information is called descriptive analytics. This has a different type of model structures in mathematics and computer science. Each of them have different prescriptive analytics. Here, treatment planning. You have a bunch of sort of health vitals and there is a disease profile. And can it say among these 5 treatment plans that the doctor has suggested, which one should the doctor prescribe? So this is prescriptive analytics. What should be done? And that's kind of related to diagnostic analysis somehow. And all of this doesn't happen by magic. These are trained by doctors. The machines are like dumb things which need to be trained. But if you train them, they can work for you better. That is how you should think about this. Okay. But these are the 4 different category of questions you can ask, trainings you can do, and different type of models exist. So this should give you a framework of what all can I do with your own specialization, your own ecosystem of problems you're dealing with. Also, there are several mathematical techniques for each of these. I talked about predictive and descriptive, the top 2. The predictive systems are called classification systems. Like, you have an image and you want to say whether the person has cancer or not, or you want to figure out if after 8 hours, right, 8 hours prediction, is there a mortality event or not. These are called classification: benign, malignant, diabetic, non-diabetic is a simple one, but basically, she may have arrhythmia, no arrhythmia in about 8 hours. So these kinds of, classification, forming the placing the person into either class 1 or class 2, and several. And then we have descriptive analysis. There's called clustering technique, grouping people, right? And so on and so forth. I don't want to go into that, but there are several mathematical models which are guiding this. The reason I put this up is that, you would have interacted with many technologies which say, okay, here's a deep learning model, you feed the data, it'll come out and it'll learn. No, it is not going to happen that way. It is possible that they do it, but the accuracy of those will not be good. Unless the person knows exactly which mathematical model should be used for which type of problem, it becomes very difficult to have an accurate system. Let me go into a next level detail. We talked about prediction. Let's make a simple game. Okay. There are a bunch of zeros and X's. Okay. There are a bunch of points. You need to know whether it's a red ball or a blue ball, let's say. And there are 2 parameters to it. Let's say one X1, X2. One could be age and another could be family cancer history or something like that, right? If age is high, family cancer history is also there, then she's likely to be cancer. I'm just making it very simple, like just 2 parameters. Obviously, there are thousands of parameters, right? So the supervised learning is you take a bunch of features, here only 2 features for simplicity, and train a system to learn the model of what is the right combination of these features which can give the answer. So basically what happens in supervised is the doctor or the expert is actually training the system, training the model, training the machine, supervising the machine, saying, here is a patient, her age is low and she doesn't have family cancer history and she doesn't have cancer. Her age is high. So it will not say high, it will say number, 57-year-old with 2 family cancer history, she had cancer. So this kind of data with the answer, with the label is given to the end user, to the model. Sorry. And now the question is, there is one more with the lower X1 and a lower X2. Where does it belong? Very simple. You just map in this XY and then say, oh, by the way, this one is very close to the blue ball, so she is not cancer. That's all is happening below. Very, very simplistically speaking, what's happening is there is a model that is built below in a way that all the things, all the records that are being trained, used in the training set, are mapped into some kind of a dimensional aspect like this. Simplistically, I've taken 2, it will be 1,000, right? It's very complex. But whichever is the closest cluster that it falls, that is the label. This is what K means, clustering. So this is one of the methods used for supervised learning. There are many, many methods used. This is one of them. This is supervised learning. This is the classification learning. This can actually, these type of things can be actually used for predicting disease and no disease. Then we call as unsupervised learning is this clustering, descriptive aspect I told, where again is X1, X2, but they don't know whether somebody is cancer or not. You just give a bunch of people and say, I have these people, make sense of them. I mentioned that example. Same way here, what happens, all the parameters and profile information of these people are taken. And it's plotted on like this n-dimensional space or a 2-dimensional space here. And then whoever comes together, you kind of group. This is called a common cohort, similar cohorts, right? And so this grouping is also a learning, right? In many cases, you do not know that there are a bunch of patients here, this type of, features and this type of features. So that is what a clustering does. Clearly, you're seeing the supervised learning has more use in a medical scenario. Unsupervised learning, for example, you're using for video recommendation, right? Which channel to switch to or something like that, right? Which movie you would like in future. So those kinds of cases of which book to read, buy next, Amazon. And so you may like this product too. You may like to buy this. No? All that is happening using unsupervised learning, because there are a bunch of parameters of the patient or the user or a user. They take online browser and group them together. And if you fall in this same group, and they'll see what did this whole bunch of people buy next, and they'll say this may be something that you want to buy. So unsupervised learning has several applications, but more applications of supervised learning is what you're going to see in healthcare. And we'll go more into it. So supervised learning is also called classification, I mentioned. So what happens here, just to go into the next level detail, there is an input, let's say a mammography image. There is a label already. There is a bunch of experts, very good expert doctors who have reviewed and said, yes, there is a lesion here. So the label is the lesion or malignant or benign or no normal, right? That label along with the input is given as a training set. You have to do like thousands of them, right? You give it to the machine learning model. Features are extracted. We look at how many dense regions are there. What is the shape of the dense region? Remember, if any of you are radiologists, you will actually know what kind of features which will allow you to actually say whether somebody is malignant. Speculations on the boundary, hypoechoic mass in the ultrasound. All of these are features that you are able to see, and that a machine can be built to extract these features. It becomes a feature array like this, the center one. And this is fed into the machine learning model. The machine learning model takes all these labeled data, we call it. The training set, it has labeled data, the person's image and whether she was cancer or not. And this gives out what is called as a classifier model. And we'll see more about that. Then when a new person comes in, the same classifier model will help you say whether there is cancer or not, or give an indication of that. There is, for the new person, you don't need a label. You just want the classifier model, the machine, to actually say predict. This is how a classifier works. Lot of training data will make this more and more better. It's just like a doctor, right? More and more experience, more and more sample cases you see, you become more and more experienced. That is what we are trying to model here. But nobody can replace a doctor. But it try to do it that way so that there will be like another robo doctor which can help you make the decisions, reduce the misdiagnosis, and make you do the decisions much, much faster and improve your productivity. So this is the classifier. And there are different mathematical ways of representing the data and the model that you've learned. For example, simple thing, right? In your high school math, we talked about a line, x is equal to y equal to mx plus c. They said if you have 2 points, you can draw a line, right? And if there is an x coming, you can read out from there what is the y value. It's a very simple line model. It's called a linear regression model. Learn this line, and if somebody has that x parameter, you can read out the y. Like that, I'm simplifying this very, very much, but this is called model-based learning, right? You actually build the model and it's kind of curve fitting kind of thing. And it can be very, very complex, Gaussian generative models, and there are several models here, but it's a model-based learning. Using this training data, it learns a mathematical model, mathematical function. And when the new data comes in, it reads out of this mathematical function. Many classifier models use this method. There is another method, is what is called as discriminating classifiers. So you have a bunch of blue balls and red balls. An easy way of putting them separately is to draw a line and say all balls here, red balls here, blue balls there. And when another ball falls, it falls here, it is red, it falls there, it is blue. But what is the separation? All of these features I talked about, like I talked about an x1, x2 last time. Think about it in 1,000 folds, right? Because a computer can do a lot of operations, it can look at it 1,000 folds, but I'm just showing in 2 folds right now. So with 2 folds, anything that falls here is red, anything that falls here is red. So again, for the example of younger age group, no family cancer history may be here, like that, right? You can separate it out that way. And this is called discriminating classifier. Here what happens, the machine learning actually learns this line to separate. Where is it? How bent it should be, how straight it should be, all that. Or should it be single line or multiple lines like this? These are called classifier boundaries, which is learned by the mathematics. Okay. And final piece, and now all the math is gone. A more simpler example, a different type of classifier called decision tree classifier. What is a decision tree classifier? It's a rule analysis based classifier. I'll take a simple example. Let's say I want to know, is it raining? It's a very, very simple example. I want to know, is it raining? And it's a machine wants to know, right? Anybody can look at it and so on. The machine will say, okay, it'll ask you 2 questions. The question we want to ask is the grass wet? Is the grass wet? Is what the machine is trying to understand. For that, it will say, is it raining? Then the grass can be wet. Or is the sprinkler on? Then the grass can be wet. So you'll see that if it's raining, it's most likely 95% the grass is wet, because there could be some shed on or something and the grass is covered. So it's not. If it is not, and if the sprinkler is on, then there is a possibility that it is actually red. So this wet, right? So this is how a simple thinking can be. Two questions we are asking: is it raining? Is the sprinkler on? And the machine can predict whether the glass that you're talking about is wet or not. So this is a very simple decision tree, and you can make many levels of this. So similarly, you can say, is age between the bracket this, and then is the family cancer history? Is she postmenopausal? Is she is she having some abnormality in the lesion? Is there a complaint? Is there a nipple discharge? So all of these different questions can come in, and then you could have a risk scoring. You might have seen many risk scoring. That kind of works in this rule-based model. And this, when it becomes more complex, it's called a random forest. You have multiple such decision trees coming together, it becomes a random forest. This is an excellent tool to actually determine cohorts of people together who have a common characteristic. Because it's not like, again we say, cancer is not, or any of the diseases, you can't say this 4 parameters you're done, right? There could be 1,000, 20,000 parameters you may have to look at, and maybe a smaller group of each of these will go into the same medicine, right? So this is basically allowing you to live different decision trees to come together. It's called random forest. The good news is you don't have to build this by hand. The good news is all you need to do is what I mentioned before: give a bunch of training data and the label. The machine is going to learn this whole tree or whole forest. The machine is going to learn. That is a random forest classifier. But this is what is happening internally, so that you know exactly how the machine learning model, how the AI is actually working. I've simplified it and given this in multiple modes. Any of these tools, any of these methods may be used by your AI model, right? And when this is done in thousands of parameters, 10,000s of data set, then the analysis is likely to be close to accurate. And you can use that as a helping tool for you. So that is how the interiors work. Many of you would have heard about deep learning and are using deep learning. Is AI deep learning, and so on and so forth. There are different methods of deep learning. It's called convolutional neural networks, RNN, CNN, VNet, UNet. There are several nets. What is this net? Deep net, right? The net is very similar to our net, which is there in our brain. Okay. So we have the neurons. They're all connected to each other, right? And signals pass from one to another. What a deep net tries to do is artificially create this neural network. ANN is called artificial neural network. There are different varieties of that. So when the training happens, I mentioned, you have to say if I feature, it's the age, family cancer history. Many times you don't know what those features are. The machine wants to learn the features also. If everything the doctor is telling, what is the machine learning, right? Can it learn the features to look at? When you give a mammography image, can it say, why don't you look for irregularity? Why don't you look for density differences? Can it suggest that? That is where the deep learning comes into the picture. It's called feature learning. It's not just machine learning. It also does feature learning. Feature is not given by a doctor. Feature is not given by a computer scientist. It's actually learned. And typically machine learning is great for video, audio, images, and these kinds of patterns that the computer is able to look at. This requires a huge amount of data for training. So when you look at multiple such data sets in the training, you can actually look at abnormal pattern and normal pattern. Of course, this also is supervised, so you actually have to say whether somebody's cancer or not. But if you have 1 million mammography images and labels of whether she was malignant or benign, this can actually learn. And you don't even have to do the feature parameter which I mentioned. It automatically you feed in. Of course, a lot of fine tuning is required. This is called layers. How many layers you want to, what should you structure the layers? So those are all the complications that come in. But deep learning, remember, will help you learn the features only, right? At the end, what happens? It learns the features, and it could be not really useful medical features. It may look at half BP or some vague feature it may learn, right, which doesn't have significance. So deep learning based systems are difficult to interpret, difficult to explain to the doctor. The machine learning model will come say, yes, she has cancer, but the doctor asks why. I don't know, the deep learning model is saying. So that is not going to work, right? So you need to have an explainability. So there is a lot of research that's going on to how to make this explainable. So anyway, so these are different ways in which these AI models are working internally. It may look too deep and mathematical to you, but if you know this, my aim is to say, okay, knowing these are the different methods, you may think, yeah, maybe there's some sanity happening. There is some real stuff that is helping me do this. I hope that you got that picture. But because this is all very, very abstract, what I'm going to do now is say, okay, is there one application where you have used machine learning and you can tell me what it did? And that is what I'm going to do now in the next 10 to 15 minutes, where I'll take this example that I have been very, very closely involved with in the last 4.5, 5 years to develop a completely from the ground, innovated in India, machine learning based analysis solution for breast cancer using a completely different type of images called thermal images. And I'm going to explain this because it has several implications and several learning. And using this example, I will be able to try and relate to multiple things you heard so far from a theory standpoint. And at the end, I'll be happy to answer any questions which are related to your own applications or generic AI or machine learning. All of you know this, but I just want to remind you that breast cancer is one of the largest causes of cancer deaths, largest cancer killer. 680,000 women died in 2020 because of this disease. 1 in 17 women globally are likely to have this abnormality. 1 in 7 in US, as per the statistics. Developing world is at higher risk for breast cancer and it also has lower survival rates. In India, for example, survival rate is just 50 to 60%. So this is alarming because many of you know breast cancer is one of the most curable or manageable diseases of all cancers. Only thing is that early detection is very, very important. Why is early detection not happening? Many of you may also know that there is this dense breast issue which stops mammography from enabling early detection. You see, the first one is a fatty breast of, let's say, 60-year-old. This is a dense breast of a 40-year-old. Dense breasts have a lot of white because of fibroglandular tissue and X-ray. Mammography is an X-ray. So an X-ray already shows dense breast as white, dense as white. So the whole fibroglandular tissue comes in as a white. And how do you find this white cancer? How do you find this white cancer? So that's an issue. Sorry, I'm not able to show it. But this can be shown, but this one is that's meant for affordability, accessibility issue when we talk in world, sorry. Because of exposure, it can only be detected once in 2 years women. All this if you're on ultrasound, breast screening in a preventive or a regular newer. So we said if younger women cannot be detected with the breast cancer, detected of breast cancer using mammography or X-ray, is there another modality? We looked at thermal imaging. Thermal imaging is very controversial in general. It was FDA approved as an adjunct modality in 1984 itself, but it's not used in every place. Thermography. Thermography basically measures the temperature variations on many imaging images high temperature people. But there is a lesion, there is high because cell division has vascularity in the region. So temperature variation. You can see 4 women here. This is a normal lady, class 1. This is an abnormal lady, class 2. Abnormal, actually malignant lady, because there is a focal increase in temperature here. And this is biopsy proven to be malignant, and hence it is class 2. The ground truth is coming from biopsy. These 2 are people, they have red spaces, but they are just benign. They form into the class 1 case again. So now we start with this kind of a training set. And then we actually use different features. I remember the first slide, right? We send this with the images and the labels, and then different features like demography information, asymmetry in patterns between left and right side, thermal distribution, vascularity of this, which is also a new algorithm we have developed. And all of that is taken out and used as a feature. There are several other things that are, let me finish this, right? These are used as features. And then the labels are basically the benign and malignant. The features can be even more further explained by saying boundary features could be deviation from a circle, irregularity, all of these, vascularity, what is the length of the vessel? All of these are thermal features that are extracted, and then the results will be generated. Then you obviously, what the machine predicted, you have to compare with what the radiologist said or the pathologist said after biopsy. And when we did this, we were so surprised that this machine learning model could actually give 100% sensitivity in asymptomatic women with only 7% false positives. Specificity is 1 minus false positive or 100 minus false positives. So false positive is just 7%, and we had a sensitivity of 100%. And because it doesn't depend on density, it turned out to be better sensitivity than mammography in dense breasts as well. And it is better than manual thermography because it now has less false positives, which was the problem with earlier. So this was an excellent experience of taking a real problem and making it work in a prospective study. And this has been tried on 34,000 people. We are published in multiple forums, including ASCO Breakthrough Summit, where we actually compared vis-a-vis a very systematic trial on 769 patients. We compared with mammography, and also published in Global Oncology and those kind of journals. So essentially what has happened is we have used artificial intelligence algorithms on these thermal images to generate a report. The report suggesting to the doctor whether it is likely abnormal or not. In fact, there is a mobile app in which this report goes to the doctor. Only the doctor, the mobile app is called Niramai Doctor. He sees all the patients in his unit there and with suggestion of whether it's malignant or not. And the doctor can review with this and any other clinical finding to say whether she's actually malignant. So this was a huge learning experience for us to say what are the different stages and what and how to actually use machine learning in a clinical workflow. First, like I mentioned, you have data. Identify what data you have. With this data, ask the question, do you want a diagnostic use case? You want a predictive use case? You want a descriptive use case? Or you want a prescriptive use case? Determine what is the use case you want for your best function. How do I get hold of this data? How do I actually, is it in the PACS system? Is it in my EMR? Is it actually in notes? There are several ways, right? Figure out how you actually get the data. And most important is the privacy angle to it. Is it anonymized? For example, all of these are, there's no face, just thermal images. Patient ID, no name, no email ID. This anonymization is very important because the data can go anywhere. So you have to be very careful about privacy of the patient. Next, annotation, whether this mammography or thermal imaging is actually malignant or benign. Then the fourth one, model development. I mentioned multiple, beautiful diagrams before, discriminative with a line separating blue or red. Or are you learning these curves, so that you can predict? Or are you using this forest, the model development? Which model gives best result? Then there should be somebody else who will come in and say, is the algorithm doing right? Because somebody could say, if first patient say positive, second patient negative, you have to be very careful. It's called non-generalizable thing. So somebody has to look at the algorithm and make sure that it's not goofing up. And you have to do a multi-site validation, the prospective validation of these models in one or more hospitals. We have done validation in 3 hospitals just for the 700 patients. Of course, 35,000 are coming from 70 different hospitals. Then regulatory approvals, right? Regulatory approval from ICMR or CDSCO, DCGI organization in India. Europe is CE regulatory body working. And then, of course, US FDA. And each of these countries have different regulators. So if a medical device is to be taken to a different country, their regulatory approval is required. Once it's approved, how do I integrate into my current clinical workflow? You're already doing mammography. How does it come and sit here? Who all and how all can I train these doctors, the technician, and so on and so forth? And when I put this into the system, will the user, that the doctor accept this as the right modality? Do they agree with the accuracy? Do they really find it useful? And then release it, make people use it, and then figure out what are the post-market feedback that you're getting. So any machine learning used in a clinical workflow or a new device has all of these 10 phases. So it's a very complex process. And I'm very happy to say that the solution which you just saw has gone through this whole thing, and it is very well accepted in India with Apollo clinics and HCG and many other cancer hospitals also using it. So you did see now how a use case of breast cancer detection is saving lives using artificial intelligence. Thanks a lot. I'll be very happy to take questions.
Doctor, we have a few questions in the chat box. So I'll be reading out.
Yeah.
So first question is, what does the future of healthcare look like for populations which are not yet tech-savvy doctors?
Very good question. First and foremost, AI is actually used in many, many places already. Healthcare is the, last, if I can use the word literally, one of the last to adopt because of two main reasons, right? One, and most importantly, you're dealing with the lives of people. Unless the AI is really, really good, you cannot adopt. Second, of course, as you said, many doctors are less tech savvy compared to like normal computer kind of people, right? So what is done usually is, I say always as a computer scientist, right? If you want less tech savvy users or less skilled users for, let's say, technician side, your tool has to be smarter. The interface has have to be simple. As doctors, I have actually taken you through the internals of an AI model. What are the complexities which is going? You don't have to deal with that complexity. All you need to deal with is work with the engineers, work with them, partner with them to tell them. Like, for example, we generate a report and we were saying thermobiological score, areola score. Dr. Sudhakar sir said, see, these are all good, these are scores, but I usually use BI-RAD scoring. Can you give me BI-RAD? I said, yes. So you have to work with the engineers to tell them what is useful because they don't know anything about medical science. You are the expert. So where you have to help this whole system and make this useful to yourself, to the people, to the citizen, to the patients, is that you work with them and say, this is what I need. Obviously, you can't bring moon to the ground. So whatever I told you so far would have given you an indication of what is possible, what is not possible. So using that framework, you work with the engineers to say, this is what I want. They have to give you. You don't need to learn coding to understand and use AI. You need to make sure the people who are giving you AI give it to you in a form that you can use it. You are the God. You have the power to ask. My only request is that is how AI should come to you. And engineers are ready to do this. You only have to be open enough and say, yes, I'm going to try. Show me what you have. Oh, by the way, you showed me this. These are the changes I need. So you have to be open and give feedback. And that's all is needed.
So, Doctor, the next question is, what will be the role of hospitals in future, let's say 10 to 25 years from now?
Oh, yeah. Hospitals are always there. See, machines can never replace human beings. That is never possible. This is a one line of assurance from a doctor. You have a cancer report. Machine will say, BI-RAD 4, a follow-up with ultrasound recommended, red. No, it's not going to work. This needs a doctor who can explain to the patient what this means, what are the different treatment options, and all the complicated things cannot be understood by a machine. There are 25,000 different common diseases. We cannot have 25,000 machine learning models. Only common diseases can have. There's so many complications. There are comorbidities. Individual diseases is what this will actually detect. So all of this complexity, you are the people who can actually handle it. These are only tools. These are only tools to help you do your job better. That's all. So the hospitals will exist. Of course, the idea is to do preventive healthcare outside the hospital. You have these wearable devices. You have this home monitoring, equipment such as BP instruments, sugar, glucose measuring instruments. Many houses already have it now. So allow them to do those things there. Preventive, the wellness kind of, initiatives or interventions, can let that be done outside. Critical care is where the hospitals can come in, or something that's abnormal, then you can come to the hospital, right? So that way there is a good load balancing that's happening. You don't have people running and coming to you and forming long lines when a critical person is behind the line, right? So the right people who require your attention should get the right attention from you. as opposed to simple cases which can just be monitored, can be monitored. Even while monitoring, a machine can help you. It's actually monitoring, and suddenly you see a spike in the BPs. Immediately it can send you a message where you have to come and see. So you will only be seeing cases which require your attention. So hospitals will be more productive, less crowded with unnecessary patients, and making the same type of money even after 25 years.
So, doctor, the next question is there any evidence that AI is more accurate than doctors?
See, there are many criteria. Okay. There will always be a doctor which is better than the machine. There will always be an expert who has 25 years of experience, who's never made any wrong diagnosis. And that person will be better than the machine. But when you look at a common doctor skill level, right? A junior doctor, mid and senior level like that, there has been proven techniques where, for example, it depends on how complex the imaging is, particularly in medical imaging. I gave this example of actually, I didn't go into a lot of details, but we have done an analysis of manual interpretation of thermal images versus, thermalytics. We have found 70% better positive predictive value by the machine. Google has done a study on mammography, and they found 10% increase in sensitivity, that is reduction in false negatives. Why? Because it's a human limitation. You cannot look at 4 lakh temperature. It's nothing that, think about this. Why do we use calculators? Why didn't we mug up all the multiplication table, right? And why don't we do all the computation, additions, everything? Why do you need an Excel sheet? Because you can do in the mind, of course, but there's a limitation. Cognitive ability has a limitation. When the task of pattern recognition has 4 lakh temperature points, and the task is to figure out any small abnormality, then it's a cognitive load. Some superhuman can do it. But when a machine is trained to do it, it has the power to do it much faster. Think of it like a calculator. That's it. Calculator will only calculate. It doesn't know what it is calculating, honestly. That number only you know. So use it like that tool. And yes, it has been proven both in for example, in breast cancer, both in thermal imaging and breast mammography, that it does have better sensitivity and specificity than a group of doctors. We're not saying all the doctors in the world. Usually what happens, maybe if 5 doctors are asked the question, some of them may say wrong, some of them may say right. And the maximum voting is taken, and that is when it's compared. Sometimes 15 doctors are used. So it will be a mix of skill level. Those kinds of studies exist. And here again, it's only one view. The doctor is using this as a second opinion before he or she gives the reading or a final impression to the patient. Why? Because what if the doctor missed a small lesion and it appears within a month as a big lump? The doctor will get sued, right? Especially in the US, these are very, very harmful. So they actually prefer to do a quick check with an AI model. Tell me, are you finding something? It'll mark. Okay, then you zoom in and say, yes, it does look. No, you're saying wrong. We'll ignore. So you can also ignore the output of AI, but it'll just give you a second look at it so you don't miss it. So it's all about improving your diagnostic accuracy, your capability, your skill of doing highly cognitive tasks. And there are thousands of patients waiting for your attention. It's also humanly possible that there will be fatigue and there will be some errors. But helping in those cases is what the AI can do. Next question.
Doctor, next question is, as a doctor, we don't trust machines at times because they can go wrong. How do we as a medical community come together, use AI?
Yes. So that is why it's very important to have explainability. The machine will say, you only think of it like it is reminding you. Those of you who have adolescent children, you'll know, right? As a parent, you can only advise. What they do is what they do, right? But it's not that whatever the parent says is good for the person, right? It's exactly like that. It's a suggestion. You can look at it and then say whether it makes sense. It is really true. Look at different other clinical parameters and then take a call. But again, just to repeat, it's only there to help you make a better decision at a faster pace. That's all. How to come together, right? You can actually do clinical validation together. That's why multi-site trial is very, very important. I'm very thankful to many doctors. We are working with 60 plus doctors. It's not possible. It's not a single computer science kind of a thing. It's a partnership between doctors and engineers that can make this happen. We have to come together. Only request is be open. It's not here to take away your jobs. Doctors are real gods who can make the final decision looking at multiple parameters. My daughter is also studying MBBS, and I know how much of studying of literature and different how complex the body parts are and so on. So all that only It is here looking at an outside in perspective and giving you indications of something that in case you miss, you may want to look at it. It's a relook mode. That's it.
So, Doctor, the next question is, what are the future outlook for rural India medicine?
Yeah, that's my favorite question because I'm a strong proponent of healthcare for all, high quality healthcare, affordable healthcare, accessible healthcare for all. And I firmly believe AI can help a lot. There is a huge lacuna of number of doctors in rural areas. One doctor serves 1,000 families. Now, with this, how do we enable healthcare in rural area? That is where I think even if the AI models are mostly correct, 90% accurate, if you can give this to a health worker, not to make a diagnosis, but just the screening, saying whether this person requires to be brought to a hospital now, immediately, prioritize the patient, triaging, a red, yellow, green, triaging. AI models can be definitely used to do that. In fact, we do that. We provide these red, yellow, green models to health workers and do a quick screening along with hand examination so that we can bring suspected patients to the hospital for an ultrasound and then, of course, MRI required and biopsy with the doctor's consent, right? And guidance. So this is where AI can be a huge help in rural areas to be a tool that a health worker can use to triage the patient and bring her back to the high infrastructure. And in a city, AI can help in becoming a helping tool for the doctor so that they don't make mistakes because they are in pressure, helping them be more productive, do decisions in shorter time, as well as free up some time for you to live a nice life in addition to serving people. So that way AI is a boon both in rural and urban areas, according to me.
Doctor, so the question is, what are the key risks that can arise from using AI in healthcare?
Yeah. So the risk is that, which we have to be conscious, it's an excellent question, is that you get so dependent on AI that, you always are saying yes to what the tool is saying. So that is the small risk you have, right? Again, AI is not replacing you. It's probably going where you cannot go, but it's not replacing you. So because of that, you always remember you still have to make the decision. So I think that's the reminder, which is the only thing that, we have to make sure, because it's always easy to say, oh, this is saying yes, so yes. Yes is fine because there's always a diagnostic test which will help and finalize. But a no is a no, like false negative is something that you have to take. So that is the only risk I see. Thank you very much for the great questions.
Yes.
And really enjoyed speaking, and hope you enjoyed with this content as well. Thank you so much.
Yeah. So thank you, Dr. Geetha, for your valuable insights on this interesting topic. Thank you all.
Thank you.